Dear students, in the last class we have studied about the technique which is known as the symmetrical component and the various model of transmission line, generator and transformer during the symmetrical component. Now we will apply this symmetrical component technique for the analysis of unsymmetrical fault. Basically three types of fault are there: single line to ground fault, double line to ground and line to line fault. For analysis of unsymmetrical fault, we have considered a faulty system. There is a three lines, phase A, phase B, phase C. At the point F, the fault will occur and the current from outside the line is IA, IB, IC, and the voltage between line and ground is VA, VB, VC. So in that case, suppose from the looking to the fault point F, we can divided the current into the three part. Current IA is divided into three part: positive sequence, negative sequence and zero sequence. And voltage: positive sequence voltage, negative sequence voltage and zero sequence voltage. So as we have studied earlier, the sequence network seen from the fault point F, it is IA1, voltage VA1, fault point F IA1. And we have studied that the EMF will be shown or generated only in the positive sequence case. So it is denoted as EA, impedance Z1, positive sequence impedance, and the fault point F, it is the voltage VA1. Similarly, IA2, VA2 point F, it is Z2 point F, VA2, and IA0, VA0, so Z0, IA0. So this is the model of the sequence network as seen from the fault point F. This is also known as the Thevenin equivalent of the sequence network as seen from the fault point F. So these three networks are used for the analysis of the unsymmetrical fault. There are three derivation, and generally one derivation is always asked during the university examination. First is single line to ground fault derivation, LG fault, double line to line fault, and double line to ground fault. So first we will consider the single line to ground fault. You have to follow some best steps to make the derivation of this fault. First of all, you have to draw the diagram of the fault. For example, this is single line to ground fault. Then we have considered that there are three lines: phase A, phase B, phase C, and the fault is occur at fault point F in the phase A, which is grounded through the fault impedance ZF. The current in the outside the fault point F, IA is IA, and as there is no fault in B and C, so IB equal to 0 and IC equal to the 0. So first of all, you have to make the diagram, and from the diagram you have to write the given condition of the fault. What is the given condition here? Condition is that IB equal to 0, IC is equals to 0, and VA is equals to ZF into IA. Now from the second step, which is the written the equations from the fault diagram. The third step, you have to write the symmetrical component of the fault current and the voltage as well as. So IA1, as we know that we have already derived the uh, transformation of the symmetrical component from the phase component to the symmetrical component. We have directly applied the equation IA1, IA2, IA0 is equals to 1 by 3, 1, 1, 1, 1, 1, alpha square, alpha, IA, IB, IC. In this case, IB equal to 0 and IC equal to the 0. So when you solve this equation, this will become IA1 equal to the IA2 equal to the IA0. It is equal to the 1 by 3 of IA. Similarly, you have to make the relation between the symmetrical component of the voltage. VA is equals to ZF IA. So VA is the sum of VA1 plus VA2 plus VA0. It is equal to the ZF into IA. And in terms of symmetrical component, IA will become 3 IA1. So it will become 3 ZF IA1. So this is the third step, that you have to make make the relationship between the symmetrical component of the voltage and current with respect to the phase component. Now from third step you have to follow the fourth step, that you have to make the connection diagram of the symmetrical component which will satisfy this relation between the symmetrical component of the current and voltage. Then what is the relation? That a positive sequence, negative sequence and zero sequence current is equal to the 1 by 3 of Ia. Means this equation shows that the sequence diagram of positive, negative and zero sequence component is in series connection. Similarly, Va1 plus Va2 plus Va0 is equals to Zf Ia. We know that in the series connection the voltage will be added. So these two equations suggest that the diagram of the sequence component is in series connection. So we can make this diagram from the equation 11.1 and 11.5 and 11.6, that we can make the series make the sequence component in the series fashion. So Va1, Va2, Va0, this is in the series. If we draw the Thevenin equivalent, then the positive sequence circuit can be written as Ea Z1 into Va1, then Z2 Va2, Z0 Va0. The current is Ia1, Ia2 and Ia0, and this equation shows that Va1 plus Va2 plus Va0 is equal to the 3Zf Ia1. So we add impedance of 3Zf is here. So this diagram satisfies the equation 11.5 and 11.6. So this is the equation step number 4. First step, you have to make the diagram of the fault. Second step, you have to write the equation from the diagram. Third step, you have to draw the relationship between the symmetrical component of current and voltage with respect to the phase component. And the fourth step, you from the relation between the phase component and sequence component, you have to make the diagram, connection diagram of the sequence network. And last step, from that diagram, you have to write the equation of the current and voltage. So from this diagram you can see that you can draw the equation of Ia1, or you can find the value of Ia1, which is equal to the Ea upon Z1 plus Z2 plus Z0 plus 3Zf, which is total impedance. And Ia, you know from this equation that Ia equal to the 3 Ia1. So Ia equal to 3 Ea upon Z1 plus Z2 plus Z0 plus 3Zf. And if you get the value of Ia, then Ia1 equal to Ia2 equal to Ia0, and Va you know that Va1 is equals to Ea minus Ia into Z1. So Va, if you apply the KVL, Va1 is equals to Ea minus Ia Z1, Va2 equals to minus Ia2 Z2, and Va0 is equals to minus Ia0 Z0. So sum of these three will, you can get the value of Ia1 also from, this is alternate method. This is alternate method to calculate the value of Ia1, or you can directly calculate the value of Ia1. And if you get the value of Ia1, then Va you can get Vb is equals to alpha square Va1 plus alpha Va2 plus Va0. So you can get you can also get the value of Vb. You can also get the value of Vc. So if you find the diagram, then you can make the values of all the other items or all other parameters of fault current Va, Vb, Vc, fault voltage Vb, Vc, fault current Ia, Ib, Ic, on all the parameters. So this is the line to ground fault derivation, and in the next lecture we will make the derivation of line to line fault and line to ground fault, double line to ground fault. Thank you.